This conference will now be recorded.
Okay, now we are moving to another topic, that is Shannon's different theorems. We have already have some idea about that entropy, average code word length, channel capacity, all these parameters we have studied, and Shannon related all these parameters and derived Shannon's theorems. One is Shannon's source coding theorem, and the second one is Shannon's channel coding theorem, and third one is the channel capacity theorem, and the channel capacity theorem also known as Shannon-Hartley theorem. Okay, we can consider each. Is initially that source coding theorem, which is the Shannon's first theorem. This we have studied what is meant by an efficient code, and we derived that we comment about that efficiency of a code, and based on this Shannon's source coding theorem, which is the Shannon's first theorem. It is here a discrete memoryless source is given, and its entropy is capital H. It is the entropy of the source is H. Then average code word length of a code which is generated from that source is L. Then for a distortionless source encoding, it is bounded as, that is that H and L are related. We can say L is greater than or equal to H. That is, there is a bound to that entropy of the source, so that L is greater than or equal to H. We know when H equal to L, then the efficiency of the code is 100%. Therefore, there is a limit, that boundary bound, we can say the source entropy H, the code word length L for any distortionless source encoding is bounded as L is greater than or equal to H. Okay, that is the brief idea of that first theorem, that is L is greater than or equal to H, where here L represents the average code word length and H is the entropy of the source. Okay, therefore these two are related, and so we can say for a distortionless encoding, source encoding, we'll have to consider that H, it depends on that H, and then that average code word length. Then Shannon's second theorem, channel coding theorem, termed as the channel coding theorem. Here, a source of m equally likely messages. That is, there are m number of messages are coming out of the source, and that m is very greater than 1. It is not a the number of messages is not a low value. It is, there are large number of messages coming out of that source, and it is generating the information at a rate capital R. That is, we know what is meant by the information rate of a source. It depends on the that message generation rate, how many messages are coming out of that source, and also on the entropy of the source. That is, this capital R, information rate of the source, R is given by small r into H, where R represents the sampling rate of that messages, or the how many messages are coming out of that source, and the H represents the entropy of the source. Anyway, here the information rate R, capital R, represents the information rate of the source. Suppose there are m equally likely messages. For the probability of that each message is same, that is 1 by m, and here information rate r, and given a channel with capacity c, that is we have a channel and a source parameter information rate is given as capital R, and the channel capacity is given as c. Okay, then according to this channel coding theorem, if r less than or equal to c, if r is less than or equal to c, there exists a coding technique such that the output of the source may be transmitted over the channel with a probability of error in the received message which may be made arbitrarily small. It is here r is the parameter of the source, it is the information rate of the source, and capital C here the channel capacity, the parameter of the channel through which we are going to transmit that messages coming from the source. Then if r is less than or equal to c, that is that information rate is less than or equal to the channel capacity, r is less than or equal to c, then there exists a coding technique such that the output of the source may be transmitted over the channel with a probability of error in the received message which may be made arbitrarily small. This with less probability of error, we can have a coding technique so that it is transmitted over the channel. The condition is that r is less than or equal to c, where r is the information rate of the source and c is the channel capacity. R less than or equal to c, then only there exists a coding technique such that the output of the source may be transmitted over the channel with less probability of error. Okay, here a source and channel information rate r is the parameter of the source, and capital c is the channel capacity of the channel, a parameter of the channel, capacity of the channel. Then we can have a coding technique, there exists a coding technique, it is possible to generate a code so that the messages coming out of from that source can be transmitted through the channel with less probability of error. That is the idea of that uh, Shannon's second theorem, which is the channel coding theorem. That is r must be less than or equal to c, r less than or equal to c, where r is the information rate and the c is the channel capacity. It is here r less than or equal to c, then only it is possible to transmit information without any error if even if noise is present. That is the uh, idea of that Shannon's second theorem. That is, if r less than or equals to c, it is possible to transmit information without any error even if a noise is present. Then we can have a negative statement of this channel coding theorem. That is the Shannon's second theorem. The negative statement of this theorem can be stated as: given a source of m equally likely messages with m greater very greater than 1 and a channel with the capacity c, which is and here initially the source of m equally likely messages with m greater than very greater than 1, which is generating information at a rate r the same, and there is a channel with the capacity c, then if r is greater than c, r greater than c, that is the information rate is greater than capacity of the channel, then the probability of error is close to unity for every possible set of m transmitter signals. This if r is greater than c, initially we have stated, we can say that the statement of the Shannon's second theorem, channel coding theorem, if r is less than or equal to c, then we can have a uh, we can transmit the signal coming from that messages coming from the source with less probability of error. Here, if R greater than C, then the probability of error is close to unity for every possible set of M transmitter signal. That is, the negative statement of Shannon's theorem says that if R greater than C, then every message will be in error. Okay, that is, this negative statement of the channel coding theorem says that if R greater than C, then every message will be in error. If R greater than C, then every message will be in error. Okay, that's about the Shannon's second theorem, that is the channel coding theorem. This initially we have seen that source coding theorem. Here it relates the average code word length and the entropy L greater than or equal to H. That is the core of that first theorem, source coding theorem. L greater than or equal to H. L is average code word length, H is the entropy. Then coming to the second theorem, that is the channel coding theorem. R less than or equal to C, then only it is possible to have a coding technique so that it can be transmitted through the channel with less probability of error. That is, here R represents the information rate and C represents the channel capacity. Okay, then that you can say the third theorem, Shannon's third theorem, or it is widely known as Shannon-Hartley theorem for Gaussian channel. Here we are considering that Shannon-Hartley theorem for Gaussian channel. It is also known as channel capacity theorem, information capacity theorem, etc. Channel capacity theorem, information capacity theorem, etc. Then, according to this Shannon-Hartley theorem or the channel capacity theorem, the channel capacity of a wide band limited Gaussian channel is C is equal to B log to the base 2 1 plus S by N bits per second. That is, according to this Shannon-Hartley theorem, the channel capacity of a wide band limited Gaussian channel is given as C is equal to B log to the base 2 1 plus S by N. Here B is the channel bandwidth, S is the signal power, and N is the noise power. Okay, here S by N, signal to noise ratio, signal power, S, N is the noise power, B is the channel bandwidth. Okay, if all these parameters are known, then we can calculate the channel capacity using this relation. C is equal to B log to the base 2 1 plus S by N. Okay, then here the signal power is given as that is in general we can that the signal power is equal to integral minus B to B. Here you can add that limit of the integral minus B, capital B, and minus B to capital minus B to plus B power spectral density, that give the signal power. And power spectral density of a white noise is N0 by 2. Therefore we can have that noise power, that is substituting in that integral minus B to B N0 by 2, then we get that noise power N equal to N0B. You will have to note this relation, N equal to N0 into B for a white noise. from we have that relation from the basic relation that how the signal power can be calculated. Over that limit power spectral density, we can calculate that signal power for anyway n is equal to n0 into b. That is, here note that it depends on the bandwidth. That noise power depends on the bandwidth. Then we can consider the trade-off between bandwidth and signal to noise ratio. In this relation, the channel capacity b is we have the relation c is equal to b log to the base to 1 plus s by n. That is, we can say channel capacity depends on two factors. First one is bandwidth and the second one is signal to noise ratio, SNR, signal to noise ratio. Channel capacity depends on bandwidth and secondly to the signal to noise ratio, S by N. Then we can consider what happens if the bandwidth changes, increases, and similarly signal to noise ratio changes. That is, here that noise changes, what happens we can consider. Anyway, here we have the expression for that channel capacity. B is equal to C is equal to B log 1 plus S by N. Therefore, we can say the channel capacity depends on two factors, bandwidth and the signal to noise ratio. Then initially we can consider a noiseless channel. That is, that noise is zero. Then what will be the capacity of the channel? That is the first thing we are going to consider. Here we can see when n equal to 0, that S by n equal to infinity. So for channel capacity, that expression becomes B log 1 plus infinity. Therefore, it is equal to infinity. For we can say for a noiseless channel has infinite capacity. When n equal to 0, that is noise equal to 0, that from this expression we get the channel capacity equal to infinity. It is here n equal to 0, for signal to noise ratio becomes infinity. From that, c is equal to b log 1 plus infinity, therefore equal to infinity. Okay, that is the first thing you will have to note. That is, noiseless channel has infinite capacity. Noiseless channel has infinite capacity. Okay, noiseless channel has infinite capacity. Then can anyone say about the capacity for a infinite bandwidth channel? Please, from the expression, how what we can say, what will be the capacity of the channel whose bandwidth is infinity? Infinite bandwidth the channel, what will be the capacity of the channel?
Infinite.
Okay, normally we will be in a conclusion that infinite the capacity will be infinity, but here we have this relation n equal to n0 into b. That is, that noise power depends on the bandwidth of the channel. Therefore, we can say n equal to n0 into b. Therefore, as bandwidth increases, noise power also increases. As bandwidth increases, noise power also increases. Therefore, due to increase in noise power, from that expression, that SNR, signal to noise ratio, decreases. That is, as the bandwidth increases, noise power increases. We have the relation channel capacity equal to B log 1 plus S by N. Therefore, as noise power increases, this signal to noise ratio decreases. Okay. That is, initially we have considered that n equal to 0, then the channel capacity equal to infinity. Next we are considering b equal to infinity. Therefore, as b increases, that noise power also increases. Therefore, that signal to noise ratio decreases. Therefore, uh, we will not get a infinite capacity with this infinite bandwidth. This due to increase in noise power, that signal to noise ratio decreases. Therefore, there is a limit to that maximum capacity that can be obtained by increasing the bandwidth. And later we can derive that expression. Anyway, here you can take this expression for that channel capacity of a infinite bandwidth channel. It is here, if b approaches infinity, capacity does not approach infinity, the upper limit is given as c infinity. It denotes the capacity of a infinite bandwidth channel, and it is equal to 1.44 s by n0. We can derive this relation later. Anyway, you will note that infinite bandwidth channel has limited capacity. Normally we say that bandwidth, as the bandwidth increases for an infinite bandwidth channel, the capacity will be infinity, but it is not the case. Reason is, as the bandwidth increases, there is an increase in noise power also. Therefore, as the noise power increases, that signal to noise ratio decreases. Therefore, there is a maximum value that can be attained by increasing the bandwidth. Okay, therefore, the maximum value, that upper limit of the channel capacity as the bandwidth b approaches infinity is 1.44 s by n0. We can derive this expression later. Okay, that's about the third theorem, that is that which is termed as, if it is applied to the specifically to a channel with the noise is Gaussian, then we can say it is a Shannon-Hartley theorem. And the statement of that theorem, that the channel capacity of a wide band limited Gaussian channel is c equal to b log to the base to 1 plus s by n. And initially we have seen that so Shannon's source coding theorem and Shannon's channel coding theorem. In channel coding, source coding theorem, that L and H, here L denotes the average code word length and H denotes the entropy. L greater than or equal to H, that is, it is bounded like this. And secondly, that information rate and the channel capacity relation, R is less than or equal to C, then only there exists a coding technique, so that we can have a transmission through that particular channel with less probability of error. And here the channel capacity theorem, C equal to B log 1 plus S by N. And the trade-off between bandwidth and the signal to noise ratio, that is, bandwidth and signal to noise ratio decides the channel capacity of a channel. And for a noiseless channel, that is n equal to 0, the capacity of the channel equal to infinity, and infinite bandwidth channel has limited capacity. And that upper limit, reason is, as the bandwidth increases, there is the noise power also increases. As the noise power increases, there is a decrease in the signal to noise ratio. Therefore, we can say, even if b approaches infinity, capacity does not approach infinity, and that maximum value that can be obtained by increasing the bandwidth b is, that is, that upper limit we can given as 1.44 s by n0. Okay. Next we can do a problem. All of you please take this problem. The data is to be transmitted at the rate of 10,000 bits per second over a channel having bandwidth 3000 hertz. determine SNR required. Then its second part, as second part, if the bandwidth is increased to 10,000 hertz, then determine the signal to noise ratio. All of you please take this question.